meter per seconds. Calculate the distance between the layer. How do we now calculate the distance between the two layers? From the formula for echo, which is equal to 2x over t. But in this case, we have to calculate the distance. X is equal to Vt divided by 2. And we cannot split this into, this can be equal to Vt1 divided by 2 minus Vt2 divided by 2. And what we are going to use? This is for the first layer, this is the second layer. Whatever we get from here and from here is subtract. That will give us the distance between the two layers. So let's see. They all have the same velocity, 2000 for time t1 and point 2. Okay? In fact, it will be t2 minus t1. Okay? This is 1.4, this is 1.2. So it should be t2 minus t1, take note of that. So it's going to be 1.4 divided by 2 minus 2000 times t1, which is 1.2 divided by 2. So let's try and do it one by one. We are going to have 2000 times 1.4, and that will give us 2800. We can divide it by 2 straight away. We are going to have 1400 minus, what will be the value of this? For the second one, is going to be 2000 times 1.2. Okay? Everything divided by 2 is going to be 1200, which is going to be, so if we remove 1004, 1002, we are going to have 200 meter. 200 meter. Okay? And that will be the distance between the two layers. The distance between the two layers. Right now, we are going to consider characteristics of sound wave. Under this topic, the candidates will be able to identify overtones by vibrating strings and air columns, itemize acoustical examples of resonance. They should be able to determine the frequencies of notes emitted by air columns in open and closed pipes in relation to their lengths. The lowest frequency that can be found in a vibrating strings is called fundamental frequency, which is F0. Increasingly higher ones are called overtones. That is, the frequency that is higher than that of low fundamental frequency, the lowest frequency, is what we call overtones. Overtones that are integer multiples of the fundamentals are called harmonics. They are called harmonics. Harmonics and overtone in a closed and open pipes we shall be considered as we continue in these topics. Then we are still going to consider for a vibrating strings, e.g. examples, a string musical instrument such as guitar, violin, or piano, a stationary transfer wave set up in the strings as a fundamental frequency vibration is as follows. The fundamental frequency that can be found that is being set up in a vibrating strings like piano, the violin, and guitar, this is the formula. We have F is equal to 1 over 2L, okay? Then divided by, the square root of T divided by what? By L. Each of these terms have its meanings. Our F here is the fundamental frequency. This is the length of the spring. This is the tension. The capital M is what we call mass per unit length. Mass per unit length. Okay? Then we are going to see, as I've said, our F is the fundamental frequency. Our L is the length of the wire or the length of the spring. Our T is the tension in the wire. And our capital M is mass per unit length. That is, it's equal to mass over length. Mass per unit length. And we can use this formula to calculate the fundamental frequency. We are going to quickly consider the following question. Let's consider question number 1. The question says, a solo meter wire under a tension of 10 Newton produces a frequency of 250 Hz. When plugged, keeping the length of the wire constant, the tension is adjusted to produce a new frequency. Which we are having frequency 1, because we are having a new value of frequency being produced, which is 350 Hz. What is the new tension? Call this one T1, because we are still looking for another tension being produced. The frequency is directly proportional to the square root of the tension. This is the solution. What you are going to use. The frequency is directly proportional to the square root of the tension. Okay? So that F is equal to K square root of T. So that K is equal to F divided by the square root of T. That is what we are going to have. If that is the case, then we can come out and say F1 over square root of T1 equal to F2 for square root of T2. What is F1? 250 square root of T1, which is 10. F2 is what we are looking for. And then, so we are given the value of F2, which is equal to 350. Then, square root of T2, which we are looking for. So let's take it one by one. Then we can have, let me try to cross multiply this times this times this. Okay? Square root of T2 times 250 will be equal to 350 times square root of 10. So that T2 square root will now be equal to 350 times 10 square root all divided by 250. So let's look what will be the value of this. Straight away, let's know what will be the square root of 10, which is 3.162. Let's multiply straight away by 350. It will give us 1106.797 divided by 250. And if we try to divide by 250, this will give us 4.427. The square root of T2 will be equal to 4.427. But we are not looking for the square root of T2, we are looking for T2. The T2, what we are going to do is that we are going to square both sides. This, the square, we remove the square root. Then we have T2. Then we are also going to square this. So the square of this will give us the value. So we are going to have the square of this, and this one is as simple as 4.427 times 4.427. That's what it means. You square both sides, and we can remove the square root, then we can have T2. Whatever you do to this side, you do to the other side. Okay? So times, we are going to have, when we square it 2 times, and we are going to multiply it 2 times, we are going to have the value 4.427. And finally, the answer will be 19.599. We are looking for tension, that is Newton, and that is the solution to the question. Question number 2 says, a piano wire 4.5 meters long has a total mass of the wire is 0.01 kilogram and is stretched with a tension of 800 Newton. That's the tension in the wire. Calculate the frequency of the wire when it sounds its fundamental note. You remember that the fundamental frequency is 1/2L square root of T over M. That's the formula. What we are having here is mass over length itself, small m, which is mass per unit length. And that's what we are given. So this will be equal to, because we have to calculate what will be the value of this using this. We are given the mass, which is 0.01 divided by length, 0.5. And that will give us, will be equal to 0.02. 0.02. And that is kilogram per meter. Okay? That's that. The next thing for us to do is to calculate the fundamental frequency, which is equal to 1 divided by 2 times